Hi George, I hope quarantine's treating you well. This is my Physics 270 midterm, and I hope you enjoy.
Okay, let's start off with Chapter 1, Question 28. The question asks, an auditorium measures 40 meters by 20 meters by 12 meters. The density of air is 1.2 kilograms per meters cubed. What are the volume of the room in cubic feet and the weight of the air in the room in pounds?
So we know when we're talking about a 3D structure, we're going to multiply the length times the width times the height in order to determine the total volume. So in our case, we're going to multiply 40 by 20 by 12 and get 9,600 meters cubed. And when we convert that into feet, it's going to be a multiple of 35.315 feet per 1 meter cubed. So when we convert that, we're going to get a total of 339,024 feet cubed. For part 2, when it asks about the weight of the air in pounds, we know that the mass is going to be the density times the volume. And we know that the density of the air is going to be 1.2 kilograms per meters cubed, and the volume of the room is going to be 9,600 meters cubed. So the meters cubed cancels out, and when you multiply it, you get 11,520 kilograms. And then when we convert that into pounds, it's going to be a conversion factor of 2.2 pounds per 1 kilogram. So when we convert it, it's going to be 25,344 pounds total.
Alright, now let's move on to Chapter 2, Question 77. So this question says that a motorist drives along a straight road at a constant speed of 15.0 meters per second. Just as she passes a parked motorcycle police officer, the officer starts to accelerate at 2.00 meters per second to overtake her. Assuming that the officer maintains this acceleration, A, determine the time interval required for the police officer to reach the motorist, find B, the speed, and C, the total displacement of the officer as he overtakes the motorist.
Okay, so to begin with question A, we are looking for the time for the police officer to reach the motorist. So we know for the constant velocity for the motorist, we know that the position at a certain time equals the velocity times the time. And for the constant acceleration that the police officer does, we know that the position at a certain time equals the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. So since both of these equations equals the position at a certain time, we can set these two equations equal to each other. And now we only have time as the variable we don't know. So when we do this, we know that the initial position is 0, the initial velocity is 0. So what we actually have is the velocity times time equals 1/2 the acceleration times time squared. So bring the velocity to the other side and separate the t's to get t equals 2 times the velocity divided by the acceleration. And when you plug that in, you get 2 times 15 divided by 2, which equals 15 seconds is the total time for the police officer to reach the motorist. For part B, we are looking for the speed of the police officer as he overtakes the motorist. So for constant acceleration, we know to find the velocity at a certain time, it equals the initial acceleration times the final time plus the initial velocity. So when we plug all that in, we know that the initial velocity is 0, we know that the initial acceleration is 2, and that the final time is 15. So the velocity, the speed of the officer when he overtakes the motorist is 30 meters per second. For part C, we are looking for the total displacement of the police as he overtakes the motorist. Now for constant acceleration, just like we had mentioned earlier, to find the position at a certain time, it equals the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. So we know that the initial position is 0, the initial velocity is 0, so all that we have left to find the total displacement at a certain time is 1/2 times the acceleration, which is 2, times the time, which is 15, squared. So the total displacement of the police officer as he overtakes the motorist is going to be 225 meters.
Okay, let's move on to Chapter 3, Question 28. So this question says that a snow-covered ski slope makes an angle of 35 degrees with a horizontal. When a ski jumper plummets onto the hill, a parcel of splashed snow is thrown up at a maximum displacement of 1.5 meters at 16 degrees from the vertical in the uphill direction. Find the components of its maximum displacement, A, parallel to the surface, and B, perpendicular to the surface.
Alright, so in order to start this problem, we first have to determine what this alpha angle is between the displacement of snow and the slope itself. So in order to do that, we know that there is an axis this way, and this is a total of 180 degrees. We know that this angle is the same as this angle, which is 35. this angle is 16 degrees and then 90 degrees. So in order to find this alpha angle, we just take the total 180 degrees minus 90 plus this 16 plus this 35, and we find that the alpha angle is 39 degrees. So once we do that, we can then move on to answering the questions. So for part A, they want to know the maximum displacement parallel to the surface. So in order to do that, we know that the displacement max of the x on the x-axis is going to be the total displacement times the cosine of the angle, because we are looking for the total displacement in the x direction. So we do 1.5 times the cosine of 39 and find that it is 0.4 meters. For part B, they're looking for the maximum displacement perpendicular to the surface. This is very similar, except it's going to be the dmax on the y direction, and it's going to be the displacement times the sine of the angle, because we are looking in the y. So it's going to be 1.5 meters times the sine of 39, which is 1.45 meters.
Let's move on to Chapter 4, question 66. So this question says that a cannon with a muzzle speed of 1,000 meters per second is used to start an avalanche on a mountain slope. The target is 2,000 meters from the cannon horizontally and 800 meters above the cannon. At what angle above the horizontal should the cannon be fired?
So two equations that we should know before we start is that the position in the horizontal, the x-axis, is going to be the velocity times time, and then the position in the y-axis is going to be your y initial plus your initial velocity in the y direction times time, plus 1/2 times the acceleration of y, t squared. Alright, so what angle should the cannon be fired at? So we're going to start with the horizontal velocity. Is going to be your velocity, which is going to be your speed times the angle, the cosine of that, because we're looking in the horizontal direction. So when we plug that into our equation, we're looking to go a total of 2,000 meters, which equals the speed times the cosine times time. So when we solve for t, we're going to have 2 over the cosine of theta, and we're going to need that for a little later. So now if we move on to the vertical velocity, it's going to be very similar. It's going to be your speed times the sine of theta, because we're looking in this direction. So when we plug it into this equation right here, we get the total distance we're trying to travel, which equals, we're going to start here, that the velocity, which is 1,000 times the sine of theta times time, plus 1/2 times the acceleration of t squared, plus your y initial, but your y initial is going to be 0 because we're starting at 0. So we figured out that t equals 2 over cosine theta, so we're going to plug that in for each of the thetas, each of the t's, sorry, and then the acceleration is going to be 9.8 because it's going to be gravity that we're looking into. So we're going to distribute the squared here to get 4 over cosine squared theta. Everything stays the same other than we're going to distribute the 2 and the sine everything to get 2,000 sine of theta over cosine theta. And now it's just going to be basic math that we follow through. It's going to be,
We're going to multiply everything here to get 19.6 over cosine squared theta. And then we're going to multiply this side by cosine over cosine. So we're going to get 2,000 sine times cosine over cosine squared minus 19.6 over cosine squared. So we can combine those two together to get 2,000 times sine cosine minus 19.6 over cosine squared. So we're going to bring the cosine over here to this other side here to get 800 times cosine squared equals 2,000 times sine times cosine minus 19.6. And then we're going to distribute everything to get sine by itself. So we're going to get 800 cosine squared plus 19.6 divided by 2,000 cosine. So then we can divide this entire side by 4 to get 200 cosine squared plus 4.9 over 500 cosine. And then once we square both sides, we get sine squared theta equals 200 cosine squared plus 4.9 squared over 500 cosine theta squared. And sine squared theta equals 1 minus cosine squared. So we know that when we take this part of the equation right here, we can distribute this, we can bring this to this side right here, so 500 cosine squared, bring this over here, to get 200 cosine squared plus 4.9 squared equals 1 minus cosine squared times 500 cosine theta squared. Alright, so once we distribute the squared, we get 200 squared cosine to the 4th theta plus 4.9 squared equals 1 minus cosine squared times 500 squared cosine squared. So we are going to set u equals to cosine squared theta, just to make this a bit easier to interpret. So it's going to be 200 squared u squared plus 4.9 squared equals 1 minus u times 500 squared u. So once we distribute these squares for the values, we're going to get 40,000 u squared plus 25 equals 250,000 u minus 250,000 u squared. So when we rearrange it equal it to 0, it's going to be 0 equals 290,000 u squared minus 250,000 u plus 25. So now we have a quadratic equation, and we can plug that into the formula. And we're going to get u equals 0.855 and u equals 0.0001, but that value is too small, so we're going to ignore that value for now. So we know that u equals cosine squared theta, so we can set 0.855 equal to cosine squared. Then take the square root of both sides. So we get cosine theta equals 0.924. And then if we take the inverse of this cosine, we can get the theta.
It's going to be 22.3 degrees.
Alright, for chapter 5, question 70. The question says that a 5 kilogram block is placed on top of a 10 kilogram block. A horizontal force of 45 newtons is applied to the 10 kilogram block, and the 5 kilogram block is tied to the wall. The coefficient of kinetic friction between all moving surfaces is 0.200. A. Draw a free body diagram for each block and identify the forces between the blocks. And B. Determine the tension in the string and the magnitude of the acceleration of the 10 kilogram block.
So, for part A, the free body diagram of the forces, we're going to start with the 5 kilogram block. We know that there's going to be a normal force in the opposite direction to the surface of contact. There's going to always be a gravitational force, which is going to be mass times gravity. We know that there's going to be a tension force from the string holding the block. And with Newton's third law, we know that the 5 kilogram block is going to have a force on the 10 kilogram block, so there's going to be a force of AB. For the 10 kilogram block, we know that there's going to be a normal force from the surface of contact, a normal force from the surface of contact from block A. There's going to be gravity, which is going to be mass times gravity facing downwards. There's going to be the force of the 45 newtons pulling the block. There's going to be the opposite force, the force of B, that is counteracting this force right here. And then, because of Newton's third law, there's going to be a force from block B to block A, force of BA. For part 2, we're going to determine the tension of the string and the magnitude of the acceleration of the 10 kilogram block. So we'll start with the 5 kilogram block. We know that in the forces in the x direction, you're going to have the force of AB minus your tension, and because the block is stationary, it's going to equal to 0. So we know that the tension is going to equal the force of AB. In the y direction, it's going to be your normal force minus your mass times gravity, which it's going to equal 0 since it's currently not moving. So we know that the normal force is going to equal mass times gravity. Force is going to equal your coefficient of your kinetic friction times your normal force. So because the normal force is equal to mass times gravity, we can now plug that in. So our force is going to equal to our coefficient times mass times gravity. And we know that our coefficient is going to be 200. Our mass of our block is going to be 5, and then our gravity is going to be 9.8. So the force of AB is going to be equal to 9.8 newtons. And because the tension is equal to force times AB, we know that the tension is equal to 9.8 newtons. For the magnitude of acceleration for the 10 kilogram block, we're going to do something very similar. We determine that the forces in the x direction is going to be your force, your 45 newtons, minus your force of BA plus your force of B, which is going to equal mass times acceleration, because we know that the go-to equation is going to be your force equals mass times acceleration. And then in the y direction, we know that it's going to be your normal force minus the normal force from the A block plus the mass times gravity, which equals 0 because the block is not moving in the up and down direction. So we can say that the normal force is equal to the normal force of A plus the mass times gravity. So we know that the acceleration is going to equal your F minus FBA plus FB, all divided by the mass. And we know that the FB, or FBA, is going to equal, the same as over here, it's going to equal the coefficient times mass times gravity. And then with the force of B, it's going to be the normal force right here, your normal force of A plus your mass times gravity divided by M. So when we plug in all of our values, the acceleration is going to be 0.48 meters per second squared.
Alright, chapter 6, question number 29. This question asks to calculate the force required to pull a copper ball of a radius of 2 centimeters upwards through a fluid at the constant speed of 9 centimeters per second. Take the drag force to be proportional to the speed with proportionality constant, 0.950 kilograms per second, and ignore the buoyant force.
So, we know that the radius of this copper ball is 2 centimeters or 0.02 meters. The speed, or the velocity, is going to equal 9 centimeters per second or 0.09 meters per second, and the constant K is 0.950 kilograms per second, and then the density of copper is going to be 8.96 times 10 to the third. We also need to know the drag, which is going to be the velocity times the K constant, 0.09 times 0.950. So the drag constant, or the drag force, is 0.085 newtons. So in order to determine the force required, we know we're going to start by finding the mass, which we know is the volume times the density. And the volume of a sphere is going to be 4/3 pi r cubed times the density, which is 4/3 pi times 0.02 cubed times 8.96 times 10 to the third, which is going to equal 0.3 kilograms. So we know that there's a force pulling upwards we're trying to determine, and that is going to subtract the gravity force, m times g, and the F drag, and since this is currently not moving, it's going to equal to 0. So we know that the force pulling upwards is going to equal to mass times gravity plus F drag. And when we plug everything in, the force required to move the ball is going to be 3.025 newtons.
Alright, chapter 7, question 60. Why is the following situation impossible? In a new casino, a supersized pinball machine is introduced. Casino advertising boasts that a professional basketball player can lie on top of the machine and his head and feet will not hang off the edge. The ball launcher in the machine sends metal balls up one side of the machine and then into play. The spring in the launcher has a force constant of 1.2 newtons per centimeter. The surface of which the ball moves is inclined at a 10-degree incline with respect to the horizontal. The spring initially is compressed to its max distance of 5 centimeters. The ball mass is 100 grams, and that's projected into play by releasing the plunger.
So, we know from this that our angle theta is 10 degrees, our K constant is 1.20 newtons per centimeters, our delta x in which the spring is compressed is 5 centimeters, the mass of the ball is 100 grams, and then gravity is 9.8 meters per second or 980 centimeters per second. We also had to look up the average height of a basketball player in centimeters, which is going to be 200 centimeters. So in order for this problem to make sense, the max distance has to be over 200 centimeters. So we know that the change in kinetic energy is equal to the negative change of the internal energy. Total energy final is equal to the total energy initial. So for the total energy final, we know that all the energy within the system for the final is going to be your mass times gravity times your position in y final plus 1/2 mass times your velocity final squared plus 1/2 times your k constant times your x position squared. So when we figure that all out, we find out that we can plug sine of theta times the distance for your y distance final. The velocity final is going to be 0, and your x initial is going to be 0. For the total internal energy, it's going to equal 1/2 times the constant of your delta x squared plus 1/2 times the mass of the velocity initial squared plus mass times gravity times your initial y position. So we know that it equals 1/2 times your constant k delta x squared, and we know that the initial velocity is 0, the initial position is 0. So we can set your total energy final equal to your total initial energy. So what's left from this equation here is going to be your mass times gravity times your sine theta times your distance, which equals 1/2 times your k constant, your delta x squared for your total energy initial. When we plug everything in, we're going to get 100 times 980 times sine of 10 times d equals 1/2 times 1.2 times 5 squared, which equals 0.1705 times d, which equals 15. So your d max equals 88 centimeters. So the reason that this situation is impossible is because with all these variables, the total distance that your ball can travel is only 88 centimeters, and it has to surpass 200 centimeters in order for the ball to be in play during the pinball.